Okay, so let's have a look at the high-level system architecture. Basically, we have three layers: consumer contract, Wastral contracts, and the off-chain component. In the consumer contract, consumer does nothing but retrieving the result, just like a pricing oracle. It retrieves from the Wastral on-chain contracts. And imagine this contract is like a huge mapping of algorithm input and result, so which is fed by third component, which is the off-chain prover. Basically, off-chain prover listens to the requests and he executes the algorithm. He feeds the result mapping here, and while executing the algorithm, it also like generates the proof just in case, because at the same time verifier also listens all the result submissions. So if he disagrees with the submitted result, he creates a challenge associated with this result. So it also generates proof, so that if a challenge happens, they can both use their proofs. But if they agree, verifier does nothing. It's an optimistic approach. So the main part is the good part is pretty straightforward. The main problem is main tricky part is how the verification and the challenge works. So we have 5 layers as you can see here. Let's explore the first part, which is algorithm submission. Basically, first we were talking about algorithms, so we have to have an algorithm somewhere to begin with so that off-chain components can fetch. So let's imagine you're an algorithm author and you have this basic algorithm here, which is a WebAssembly file module, or like you wanna call module. So basically you upload this algorithm to globally reachable place. Preferably it should be IPFS. Then you store this IPFS address. Then you Merkleize this instructions just like here. So basically you use each instruction or operator as leaf of these Merkle tree, and you concatenate with this file hash of this whole file, so that you get like unique leaves, even if they don't build, even if the operators are the same across the different modules. So you build this Merkle tree and you store this Merkle root as well. And in the end, you take the IPFS address, file hash, and the Merkle root, and you submit this whole object to the on-chain contract as a algorithm submission object, which is a mapped registry of algorithm address and the whole registry object, as you see here. So this was the algorithm registry part. It was pretty straightforward. The second part is the result submission. But before we get into the result submission, I have to explain a couple of key concepts I'm gonna use in the next slides. So VM state is basically the raw virtual machine state of the WebAssembly execution. State commitment is an off-chain site structure holding 8 subtrees over the VM state snapshot. So basically this is just like a snapshot of the VM state. And state root, and this snapshot has 8 Merkle trees in it. And each Merkle tree has their own, obviously, roots. And this state root is the digestion of those 8 subtrees. So it's just like 32 byte hash or number, this thing. And the StepWitness, which is an important concept, the minimal data that we need to verify a single execution step. So what does that mean is, let's say you are at like step k plus 1, and imagine and you need to execute I32 instruction. So you need to know what are the values on top of the operand stack, because what I32 does in WebAssembly, it takes the last 2 elements in the stack, like which is the AB here, and it creates A plus B. So you only need last 2 elements of the operand stack. You don't care about the memory, you don't care about anything else, you just need the witness, which is the last 2 elements of the operator. That's the witness we have. And execution root is just as I said, we have state roots, a digestion of the state commitment subtrees, uh, and which also implies we have a lot of state commitments, because at every execution we end up on different VM state, which implies we have like different state commitments. And when we have different state commitments, we have a lot of state commitments to represent all the execution. And this execution root is the digestion of this whole root from state root 0 to state root n. It's just an unique representation of the whole execution trace. And as we can see here, we have the objects straight from the code, by the way. How do they look like? This is the runtime state, WebAssembly state. We have pools and everything we need to simulate the WebAssembly runtime. We have state commitment. These are the 8 subtrees I was talking about. Yes, these are the 8 subtrees. And they all have their own roots. The state root is the combination of these roots, digestion, aka. And we have the StepWitness and the execution. And the execution root is just collection of all these roots. So, and in these key concepts, what changes after each instruction execution? The VM state changes, that's for sure. State commitment changes because we don't store these stuff. So we have VM state, we take snapshot, we create state commitment, then the stuff we store is the StepWitness, state root, and the execution root in the end. So right after we create the state commitment, we construct the StepWitness for the next step, and we combine all the subroots to create state root of k and state witness k, and in the end we create an execution root with using all of these state roots. But these are the structures we store. These are the structures that are gone forever after next step of the WebAssembly execution. So if you take an example here, the algorithm we had in the previous slides, we have this two. Let's imagine we are at step 2. Yes, step 2. This step 2 in the WebAssembly virtual machine looks like this. We have call stack and operand stack and the other fields, doesn't matter. So we take the snapshot, we have the state commitment 2, we construct StepWitness, we combine the roots, these are the stuff we store, and when we execute the next step, the VM state looks like this. As you can see, since it's an reminder operator, we calculate the reminder, which is 0, and we incremented the program counter. We have this next state commitment, then we stored this new stuff again. And in the end, we create this Merkle tree of all the state roots in order to create the execution root. It's just another Merkleized digestion, let's say. So these are the key concepts of how the workflow works. So let's get back to the result submission. Okay, let's explore the result submission now. It's pretty straightforward. It's pretty easy. So in order to submit the result, this is the prover. He fetches the algorithm from IPFS. He puts into the WebAssembly virtual machine, and this virtual machine generates the step witnesses, all the state roots, and the execution root in the end, and it's stored in the prover's local machine. And also this also generates the result, obviously the result of the execution, and again the execution root, these are the same. And these two objects are submitted on the on-chain contracts. So basically this is 32 bytes, and this result is either like it's either like I32 or like I64 or like whatever the number is. Like it's just 32 bytes or like 64 bytes, nothing crazy. So, and let's get to the challenge submission, which is the second step if anything, if a verifier disagrees with the result. Let's get to the challenge submission. And how the challenge submission works is quite similar to the how the prover works. So basically, first of all, verifier needs to observe a result that's being submitted. So he always observes the on-chain contracts. When he sees a result submission, he goes to the same IPFS address, fetches the same algorithm, executes the same algorithm, and the WebAssembly virtual machine generates the exact same structures. And he stores these following structures, the same structures as the prover, in his local machine. And also, it generates execution root and result. Then when he gets the result of this algorithm, he compares the result with the observed result. If it's the same, which is the good path, nothing to challenge. He knows prover is legit. He made a legit submission. If it's different, he thinks that result is different. So prover must be lying. If not, he is lying, you know? So he creates a challenge. Obviously, if he is lying, the challenge will result in his in prover's favor. But if prover is lying, the challenge will result in the verifier's favor. So the next step is the first step of the challenge, which is the bisection game. So before we get into the mechanics of the bisection game, let's explore the motivation behind these bisection game. So our motivation is two parties disagree, so their state roots must diverge at some point. So state by state roots, I mean the snapshots, VM snapshots. So two parties disagree, so their state roots must diverge at some point. So we can exploit this to establish a consensus between them. Goal of this bisection game is to find the exact root at index x where the state root divergence begins. So the method is the bisection game, the binary search. That's why it's called bisection game, over both parties' state roots, the 32 byte hash. So the result, once x, the dispute step, is found, the step x minus 1 is the index of the last agreed state, which is an anchor root or anchor step, which will be verified on the chain with single instruction, aka one step prover. So let's check the bisection game, how it works. Let's say this off-chain prover has 8 steps, 8 execute VM states, the snapshots, which is digested by the state root to generate these 8 steps, and the same for the verifier. And let's say the prover is the bad party here, and he tempers this VM state, so the step 7, step 6, index 6. So because he tempered the VM here, it generated another hash, right? So he has these 8 steps. So, and the verifier executes the same algorithm, but with the legit execution, he doesn't temper anything. So he has these 8 steps as well. So the round 1 starts with high 8, low 0, and mid is 4. And they compared the mid, which is the same for both of them because the temper starts at index 6. So then we know that if they agree at step 4, So the dispute must have happened after the step 4. So we go to the right side of the execution. When we set the low 4, high 8, and we check for the mid again, we see the step 8 is not good, they are not same. So we know that it happened before or at the step, at the index 6. So we go back to the left side. So we set high 6, low 4, and mid is 5. And we see that they agree at mid 5. So for the next round, we obviously know that it happened after, right side of this, slice. So we go to the right again. So our low is 5, high is 6, and mid is 5 again. But since they agree at step 5 and high is 6, we know that it must have happened at step 6. So we set the dispute index 6, anchor index 6 minus 1, because dispute happens at 6. This is the first step where dispute occurs, and anchor index is 5, which is one step before the dispute index, which is the step that they both agree it happened before that. After that step. And the rounds, for the bisection rounds, it's always the log base 2 of the step count. And also, even if the off-chain prover has had the legit execution, he cannot commit those state roots on the on-chain contract, because this game is played on the on-chain. And when he claims something in the beginning in order to submit the result, he also puts the execution root. So as a Merkle tree, as we saw. So if he tries to lie here by submitting, for example, different the legit root here, he cannot pass the execution root Merkle verification. So he cannot submit any other root here. So it's the same for the verifier as well. And for the convenience, when I say anchor, I mean the component at step 5, at index 5. And when I say dispute, I mean the component at step 6. So I'll be using a lot of anchor state, anchor root, or dispute root, dispute state. So this is what I mean. And the last part of this verification is the one-step prover, which is highly inspired by the optimism one-step prover. In fact, it's almost the same. The only difference is, if I'm not wrong, optimism has an OSP for a fixed algorithm. In our case, it's not a fixed algorithm, so it can be used for any algorithm or any Merkleized virtual machine of ours, or Wastrals. So the motivation is, since both parties agree on anchor root, we established a consensus on the anchor root. We can use this consensus to compute dispute root. So goal is to find the dispute root with using the anchor witness. That's why we needed the witness, by just executing one instruction. So how do we do this? Execute anchor instruction on anchor witness. Because if we execute the anchor instruction, which is the instruction that we need to execute at the anchor index, on anchor witness, we will get the actual dispute root, which is the result. And we will use this actual dispute root to decide which party is lying. Before we dive into the details of the OSP on-chain one-step prover, let me talk about StateWitness motivation and design. So in fact, we already had anchor state, which is the virtual machine state, and if we execute one instruction on this anchor state, we would get the dispute state, which is the actual dispute state. And when we combine these roots in the dispute state, we would get the dispute root. But that's not what we do. We introduce another intermediate structure, which is the state witness, and we compute the dispute root with directly using the anchor witness. So two question arises from this implementation. Why we bother with the witnesses if we can use the states directly, because we already have those. And the second question is, how come we can compute a new root directly from the witness? So to answer the first question, the only motivation is the on-chain resource limitations. For example, the Solana has this following limitations for stack and heap. So basically, the max we can use for the heap, for example, 256 kilobyte with some expansion tricks. So let's imagine a scenario where we have like a virtual machine state with 300 kilobyte of memory, which is not out of this world. It's pretty common in any program. And let's say our next step, anchor instruction, is i32.add, which literally has nothing to do with the linear memory at all. It doesn't touch memory. It only reads from the top of the operand stack, and it writes to the on top of the operand stack. So instead of passing this whole state into the chain, what we do, we introduce the witness for anchor instruction, which is i32, and for i32 we have a reveal variables, and those are the variables that i32 that reads from, which is left hand side 4, right hand side 5, last two elements of the stack. And we have Subtree siblings. These are the siblings of these two variables in the operand pool, because this in the state commitment we have this operand pool as a Merkle tree. So we need to prove the membership of these the variables 4 and 5 to the chain by doing some Merkle proof verifications. So we have all the siblings, aka proofs of membership here. We have famous 8-subtrees, and we have the under control variables that has an information like stack height 4, because we only have these two variables, so we don't know the stack height. So this control reveal has all the necessary information. So let's get back to the second question, the design of state witnesses and the subtrees for one-step prover. So imagine that we have a VM state like this, and we have this operand state. It has like 1, 5, 10 in it, and we have the other stuff we can see, as we can see here, like a call stack, and the last elements program counter is 4. And this operand state, when we take a VM snapshot, translates into state commitment, right? So, and this state commitment has like 8 subtrees in it. So for example, if we zoom into the operand subtree, as we can see, this 1, 5, and 10 translated into a Merkle tree, and all the elements are the leaves here. So we have one null here because this is a dense tree. So because we assume that the stack can grow at most 4 elements for the demonstration purposes. So as we can see, 5 is here, 10 is here. They all created the leaves of this operand subtree. So when we generate the state witness from the state commitment, we know that the next operation is i32.add. So we only need left hand side here, right hand side here, and the last call frame, because the program counter information is stored in the call subtree. So this field doesn't matter for now, but the most important parts are the 5 and 10. These are the variables that i32 needs to read. So then we have the siblings, which are the Merkle proofs of these variables in order to verify the membership. So for example, for like right hand side, which is the second index in the Merkle tree, we have this siblings of this leaf here. And the siblings, aka Merkle proofs of this leaf, is this value and this value. As we can see, right hand side is this 0xfc and 0xd12. These are the proofs of this right hand side, so that these proofs will allow us to verify the membership. And this and same for the 5, and for the last call frame and the call frame siblings, the same logic, and the other 8 subtree roots. As you can see, we have the operand subtree root as well, the subtree root before the execution of the instruction and the control variables. And when we put the state witness into the one step prover, which is the execute step function we saw in the previous slide, it gives us the next root. So, but how does this work? So the heart of the one step prover is the leaf replacement. So basically, if we had the pure VM virtual machine state, we would have the operand state 1, 5, 10. When we executed the one instruction, which is an addition instruction, we would have 1, 15, and we would have to increment the program counter by 1. And if necessary, the other changes. So, but what does this mean, like hard leaf replacement? So since we had these subtrees in the state commitments, as we can see, if we apply this operation on the state commitment, we only need to replace the leaves here, like 5 and 10, or here. We replaced the 5 by 15 because this is the top of the stack now, and we added this null here. And as you can see, when we change these, it only affected these leaves here, and the other leaves stayed untouched. So this is where the state witness is going to take its place. So there are some places that are unchanged by this operation. So these are the other roots that change, and the subtree root obviously changed. And for example, this PC is also incremented. This has to be 5 here, it's not 4. And in the end, the state root is a digestion of this all the subtrees. So the digestion also changed, but it changed based on the roots that are changed, not by the roots that are not affected. For example, memory subtrees here as well, it stayed unchanged, and in the next state root calculation it also stayed unchanged, so we didn't have to do anything about memory. And in the schema, like the blue ones are the unchanged stuff, and the red ones are the changed stuff. As I said, this has to be 2, this has to be 5. I forgot to change those in the schemas, but yeah. And for the next step, but like this is on the state commitment, and we don't have this state commitment objects on the chain. We only have the state witness on the chain because of this resource problem. So what we do, we generate the state witness from the state commitment, and when we provide it to the OSP, it rebuilds this tree, and it doesn't have to know the exact values of these variables here. It can just fetch from the sibling to generate the partial operand tree. So it generates this partial operand tree, and because the reason why he can generate this partial operand tree, because we only need the siblings of the changed values. We don't need, for example, if this tree was even bigger, if we had any other values, right, like here, we wouldn't even need to have any like intermediate nodes or leaves here. We would only need to have the root that combines them, which is a sibling of this value. uh, so yeah, this is how we recreate this partial subtrees in the like one-step prover. Obviously, like, we don't construct the whole tree in the OSP. It would be like computationally expensive, but this is the best way to illustrate. So and this is the same logic for the other subtrees, and as we can see, we have the state root, and we do this addition operation and the OSP, and we create this new partial subtree as by changing the only leaves, as I said. And the same logic here, the other subtree stays unchanged, and we compute the next new subtree by just changing the changed intermediate nodes or leaves, and we compute a new subtree with using the siblings. And in the end, we were able to compute the next state root without touching any memory or like any unnecessary fields. So, and the OSP pipeline looks like this. We have anchor root, anchor instruction, anchor witness, and we provide these all of these stuff in the OSP. OSP first does some trivial verification and authentication, like control verification, frame authentication, like call frame authentication. Then it continues to do Subtree Recompute, the apply instruction, another like intermediate instruction we saw, and the dirty path authentication, and I'll talk about this as well. Then in the end, it combines all the subtrees, uh, the thing that we see here, in order to compute the next root. So to start with trivial verification and authentication, it's just basic Merkle root verification based on the provided data, so that we know all the provided control with the control witness, and all the subtrees belongs to the claimed root. And same for the call, the last call stack frame, the provided last call stack frame, because we always have to provide the last call stack, because this call stack has the program counter information, and program counter always changes. No instruction leaves the program counter unchanged, so we always have to provide this call stack, the last call stack, and we always have to recompute and compare the verified membership. Then after all this verification, we go to the apply instruction. So apply instruction is the function that applies the anchor instruction, obviously. So in order to execute this instruction, first we need to read left hand side and right hand side, right? But obviously we're not going to believe what user claims that right and left is. So what we do, we read the operand in an authenticated way. So what we do, we generate this partial Merkle tree in the instruction. We read this, we reconstruct this partial Merkle tree with using the siblings of these operators, and we compute the root, and we check if the root is the same as what's claimed here, the operand stake root. So if we can verify this, we know that 5 and 10 belonged to this Merkle tree, which is operand subtree, with these leaf positions. So but you might ask that, so subtree roots also comes from the StateWitness, which is from the user. So how can we trust the user to compare these roots? But that's not true. We don't trust the user, because in the previous bisection game part, they play this bisection game in order to agree on some state, and this state is agreed after every Merkle verification. So we first check that if the combination of these subtree roots, the digestion, gives the same digestion as the claimed anchor root. Basically, you can see here this line here. So we know that this subtree roots is trusted. So if we can compute this with using these claim variables in the leaves, we know that it's good. So after we authenticated the membership of these variables, we execute this instruction and we create new control operands, which is operand height 2, program counter is 5, and new operands is for the first step is for the first slot is 15, second slot is null. So, and the new call frame and the same logic here again. And then we create this transition object in order to use in dirty path authentication. I will explain what is that. But basically, we keep track of what changed and where did they change in this transition object after this operation. Obviously, it's just slot number and the leaf here. That's why it's like 32 byte. It's just SHA. The next step is the dirty path authentication. So the motivation for this step is read slots are authenticated in the previous step, right? Because whatever we read, we authenticate it by subtree, partial subtree. But what about the slots, the leaves we write on? For example, local set 0. What does instruction do? This instruction takes the last step, element from the operand stack, just like an addition, and it writes into the local stack. But as we can see here, if we only read from the locals, we don't do anything. If we only read from the operand stack, we don't do anything for the locals. So this is a problem. Why? Because you could sneak in any values without any values in the slots that we write on, because we don't authenticate them, and it's going to give us a different subtree because we don't authenticate them during the process. So in order to prevent this, this transition object also includes the new leaves that we write on as well. So when we see we've written something in the local leaf, even if we didn't read from there, we still authenticate with the partial subtrees, just like the previous step. The slots we read, slots we read, just like with the same principle. So, but there's also one like optimization opportunity here. If we read and write on the same slot, we don't have to do this verification because the read authentication is also already handled by the read part. So write authentication needs to be handled separately. And the last step of your OSP, like one of the last important step of the OSP is so in the end, after both read slot authentication and write slot authentication, we have this new operand subtree, and we do the same thing for every subtree that's affected by this operation. And in the end, we combine all the new roots that we computed by this partial subtrees, and we combine these new roots in order to obtain the next root, which is the actual dispute root that we were talking about. So finally, it looks like this. We have anchor witness provided to OSP. OSP computes the actual dispute root, which is the next root. So then we compare the claim dispute root and OSP output for both parties, for both verifier and prover, and we verify the execution root against both parties' roots, and we slash the liars and finalize the challenge. So both parties, for result submission and the challenge submission, they stake some funds, obviously. So if any party is found lying by the end of the challenge and the verification, they lose their funds. So lying is never profitable. So if challenger lies, prover gets the stack, submitted result is kept. If prover lies, challenger gets this stack, and submitted result is discarded, so you cannot sneak in anything bad. So if they both, and also the cool thing is, if they both are lying, we're gonna find it out as well, because the OSP happens on the chain. So in that case, the both of them lose their stake and submit result is discarded again. So as you can see here, the current status of the project is like this. I have fully functionally WebAssembly virtual machine that emits all the proofs and the Merkle roots, Merkle trees, subtrees, everything we talked. And I did some cross-check tests with the regular WebAssembly execution runtime. They all pass so that it's consistent. So we have off-chain prover and verifier logic, and tests with all interactions between them that we've gone through. And we have a functional OSP logic on the Solana with certain set of supported instructions. Right now we don't support all the WebAssembly instructions, but most of them can be implemented easily. And all the on-chain authentication verification tests pass, and proof of concept is ready without any gaps. And the current state of the repository looks like this. I have quite a bit files and lines. And the next step would be to optimize the virtual machine, obviously, like static analysis, like loop unrolling. Implementing off-chain clients as separate sub-moving entities, that's also another thing for production. Obviously we need to expand the OSP so that we don't run into unsupported instructions. So migrating sparse Merkle trees rather than the dense trees for most of the components. Right now we have the dense Merkle trees in order to limit the size of the Merkle trees, but it's not the way to go because they should be able to grow, you know. So, and also we need to test it with more complex algorithms and with a lot of memory operations, and we see a lot more.